Mr. Sakar, I think you're muted.
Good. So what I was saying was, are there any questions about the ethics homework, which is, I think, due today? Not today, I mean Friday, sorry.
I did have a question for the first question.
Yeah.
Do we paraphrase the given policies from our perspective, or just entirely copy the whole policies from our perspective?
So it says that there are certain things that need to be paraphrased, but there are other things that you can copy. So where it's, for instance, when it says students should not do something, you should say, I shouldn't do something, right? And yeah, you can just follow the instructions. And again, the purpose of all of that is, because we all see long, terms of use and disclaimers and whatnot, and we just, routinely ignore them. And I want to make it a little bit harder to sort of mindlessly do that exercise. Okay. So I think only very few of you have your cameras turned on. So I would like to see more of you. Great. That makes, that gives me a better sense of, whether the class is following. Okay, great. Again, if I would say if half the class is on video, I think that should be, that's a good number for me. I don't need to have everybody on all the time. So if you have to, turn it off for some reason for a little bit, that's, don't have to worry about it. Okay, any other questions about the homework? So the first technical homework is due next week, right? So do you have any questions about that? As the instruction says, you can work in groups, and however big you want the group to be, that's fine. Just make sure that you write down the solutions on your own. Okay. Any other questions? Okay. So typically in this course, we have asked students to prepare the solution in LaTeX, and I haven't done that so far, but you can expect that sometime during the semester, at least for one homework, I will ask you to use LaTeX so that you get to know how to use LaTeX. Any other questions?
Could you explain what LaTeX is for?
So all the slides I'm making, right? So all the, it's typeset in LaTeX. So LaTeX is what, professional typesetting is usually done in LaTeX. And certainly anytime you want to write math, then LaTeX is what you generally use. Okay, it's many of you, I mean, all of you know about Word, right? So Microsoft Word or OpenOffice or whatever, but those are good for doing something quickly. But when you want to produce something that has a lot of math, then you'll find that those tools are quite not that easy to use. Okay, and not only that, the quality of output they produce is terrible, right? So I can't look at math typeset in using those tools. And I'm sure if you start using LaTeX, you will, you will have the same feeling after a while. Okay, so any other questions about what we covered in the last class or about the course or about the assignments? Again, whenever you have anything that you are not following on the slides, you should really speak up, because I don't want to go on for a while without if people are not following, then I'm then it's not only the case that you are wasting time because you're not following, but I'm also wasting my time. So it's considerate to actually interrupt and let me know.
I have a question.
Yes.
So on one of the slides where it was proof by cases and there was max and there's min, I was just wondering what exactly was that? It's like I was wondering like what that represented, because I didn't really understand that slide too much.
Okay.
Oh
So
yeah,
this is the one.
yeah.
So you want to say, if you take the maximum and minimum of two numbers and add them up, right?
Mhm.
It's going to be the same as the sum of the two numbers, right? That's what the theorem says.
Okay.
And the proof by cases basically says, well, how do you prove something like this? The difficulty is that there isn't a way to simplify max or min further, right? But if you say, hey, let me assume that R is greater than S, then immediately I can simplify max of R comma S as R, right?
Okay.
So often you're going to do case splitting based on this sort of observation, right? So I have an expression, I don't know how to simplify it further, but if I make an assumption about the arguments to the function, like R and S in this case, if I make an assumption, then I'm able to simplify it further, and then that typically guides how you do the case splitting for your proof.
Okay. Thank you.
Okay. Any other questions? Right. So when you use LaTeX, overleaf is the way to go, and yeah, otherwise it's a little bit more of a pain. Probably, a year from now, most of you will have like a Linux setup. And if you use Linux, then all of these things become very easy, right? Because a lot of the software that we use as computer scientists are easily available on Linux, and setting it up, installing, and so on. Everything is a breeze. But if you are working with Windows or sometimes even Mac, it can be a little bit more of an effort. And so, especially LaTeX, because it has got a lot of pieces to it. And so if you use overleaf, then it just deals with making sure that you have all the pieces of the software package, and then things work smoothly. Any other questions?
On the homework for like the technical homework 1.
Yes.
Is it okay if we like prove something with words? Like, I think one of the questions is like, all prime numbers are odd. Can I just like say that 2 is prime number, but it's even? Like,
Yeah.
Okay.
Yeah, that is a proof too, right? So, or a counterexample, right? So that's fine.
On the homework question 3, is NAND equivalent to and not? For example, would P and
So
not Q
the problem
be P
defines the
and
operator,
Q?
right?
Yes.
Okay, so if there is an ambiguity in the definition, tell me what the ambiguity is. I'll clarify that. But I don't want to explain it because part of what I want you to do is to read descriptions like this and understand and be sure of what you understand.
There's no
So
ambiguity.
sometimes, of course, I intend to write something precise, but I fail. And the thing is neither precise nor clear. So for instance, in this problem, it wasn't my intent to, I wasn't thinking about 2 being an even prime number, and that wasn't really the proof I was expecting. But I do make mistakes when I set a problem. And, so the point is that where I do make mistakes, so do point it out, but sometimes it's not a mistake. So so if you have okay, so just ask your question again.
So would if not and it is just
So let
not
me just write it
and,
down because I
then
think
can they be
the
arranged?
English is not that clear. So I would say that, let me just write it here, right? So A up arrow B equals not of A and B.
That was a confusion there, and I tried proving that with the truth table, and I got that, but I wasn't
Yeah.
sure.
Okay,
So,
because
thank
I think again, you realize whenever something is written in English, it's always going to be a little bit of a question as to exactly what it means. So so this is why we try to use symbols, but then sometimes people the symbols
Thank you.
sometimes make it harder to read. So there's a trade-off. Any other questions?
Oh, about 3A.
About what? Sorry, I missed that part.
Yeah, 3A on the first homework.
Yeah.
Show that and, or, and not can be expressed using NAND. So is that like converting P and Q or P and P?
1 second. Now, let me pull that up so I sort of have an idea of what are we talking about? Yeah, you said 3B.
3A.
Yeah, 3A, okay.
So it's like show that and, or, and not can be expressed using NAND.
Mhm.
So is it like P and Q, converting that to using NAND, or is it P and P? If that makes sense.
So when you want to say that one operator can be expressed in terms of other operators, right? The first operator, if it takes 2 arguments, then you should say, okay, let these 2 arguments be arbitrary, right? So you shouldn't say P and P. You should say P, let the arguments be P and Q, right?
Okay. Thank you.
Anything else? Okay, very good. So there is one other thing that I want to tell you or bring up, which is related to exams. So I have a feeling that, as I said, I heard some noise about proctored exams, but I don't think it's going to happen because it's been 2 weeks since the beginning of the semester and I haven't heard anything about the arrangement. So chances are that we are going to use the lockdown browser for exams. And what I will do in the coming weeks is to set up like, uh, practice sessions, or rather practice exams, I would say, right? So where the goal is not to actually, your goal is not to answer the questions. That's not the test. The test is, learning how to take a test using the lockdown browser, okay? So we'll do that a couple of times, maybe 10, 15 minutes. We'll probably do that during the recitation, right? So you are familiar with that setup, and hopefully that won't be a significant source of stress during the exam. Okay, so that's my hope. The second related point that I want to bring up is that if we are going to do the exams using lockdown browser, then I think it is preferable to have 2 midterms instead of 1. Okay, so that way you have a chance to 2 chances to take an exam before the final comes, right? So I think it's so I think by and large, most students would want would prefer having 2 midterms because it reduces the stress of each individual exam. But if that's not true, you please speak up, and there is no consequence. I'm not keeping track of who says I don't want to take an exam. When I was a student, obviously, if a professor would say, I'll give you A without taking any exams, I would, of course, jump up and say yes, right? So it's entirely understood that that exams are sort of not something that people look forward to. So if you want to take only 1 midterm, that's perfectly understandable, but please do speak up, okay? The second thing about exams that you should, that's particularly important for students transitioning from high school to a college environment is that in college, we tend to use the entire range between 0 and 100, right? So it's not that good score is only in the 90s, right? So in my class, typically people scoring, 2 or 3 people in the class may score in the 90s, if ever, okay? So that many times it just doesn't happen, okay? And part of it is because we are always trying to give you exams where we want you to think and come up with an answer on the fly. And of course, the problems are always much easier for the person setting the exam than the person taking the exam, right? So as a result, it can turn out that some of the problems that we set are simply too hard for anybody to do. And this is why very high scores are relatively rare, right? So you should not, it should not stress you out if you take an exam and you get a 60, right? A 60 is typically a good score, okay? Of course, if everybody in the class got a 90 and you got a 60, well, that's definitely a reason to be stressed about. But in all these years that I have taught, typical class average is in the range of 60 to 70, okay? And sometimes it goes below that. 50 to 60 happens sometimes, but that usually means that I'm, I did a poorer than usual job of, figuring out where the students are, right? But a 60 is a good score, right? And so you should not feel bad about getting a 60. And again, another thing that goes on in high schools is that people are given a lot of practice, right? So you have seen problems of the kind that are going to appear in the exam many times in homeworks, right? In college, to varying degrees, you will not see this, right? So there will be some courses where, of course, you might still see that most of the questions are of the type you have seen in class or in homeworks, but very often, there are also many courses where there are going to be questions that are all going to be new, and you need to sort of apply the concepts you have learned in order to come up with a way to solve the problem. Okay, so this certainly is going to be a different experience for you, and it can be stressful, but again, you have to keep in mind that everybody is in the same boat and everybody is having a hard time. So just take a deep breath, and things will all work out in the end. Okay, so the most important thing is to make sure that you are keeping up with the class, doing the homeworks. I try to give out homeworks on a fairly regular basis so that the concepts that we teach, you have a way of going back and then checking whether you understood the concept, and you have some way of applying the concept and checking it. So, okay, with that, let me stop this long introduction and get started with the lecture, unless there are any questions.
I just have a question, like going forward, like if we need help with like after we submit a homework but we get it wrong but we don't understand it, when would it be an appropriate time to ask about it? During class time, during recitation?
So the easiest thing is you during your recitations, even before you submit your problems, right, you can raise questions, and the TAs will use their discretion as to how much to explain and how much to hold back, right? So you can certainly ask before it is due, but most certainly you can ask after, right? You can say, hey, I don't understand, I want you to go over the solution today, right? And the purpose of recitation is really to sort of supplement the lectures and help with problems and so on. Okay, and of course, in addition to that, there are office hours, so you should really take advantage of the office hours, because it's not only useful for you, but it is very useful for us. So because for me, of course, all of this is elementary material, because I've seen this for what, 30 years, something like that, right? So it's sometimes difficult to know what problems students will be facing. So when you come up and ask a question during my office hours, that gives me an idea as to what what is not getting across, and then I can come back and try to do a better job, right? So this is really important. So please speak up. Anything else?
I know it's a rather silly question, but is there any chance that in-person office hours, if you'll ever be on campus at all?
Yeah, good question. Yeah, so I don't expect so, but you will get used to this online. It does work quite well. The only issue might be that sometimes the tool doesn't work well, and I might not notice when somebody is waiting for me. And if you ever find that to be the case, try sending me an email. Okay, so if I don't notice it in one place, then at least I'll hopefully notice it in another place. But once you are on, I think it does work well, right? So we are all getting better at this over time. So so I think it'll be fine. I don't think we are going to do this in-person office hours this semester.
All right, thank you.
Okay, very good. So let's get to this unit summary. So This unit was about propositions, right? So proposition is something that is either true or false, right? So it's a statement that's either true or false. And we talked about claims, conjectures, and theorems, which are all examples of propositions. And the difference being that a theorem is something, is a proposition which has been proved, right? We talked about logical formulas. How do you take English statements and convert it into logical formulas, which involve conjunctions, disjunctions, and negation, implication, these logical operators over propositions, right? So we take an English sentence, break it up into statements, each of which can be thought of as a proposition, and then the entire English statement becomes a logical formula. Okay, so we talked about truth tables. How do you construct truth tables? How do you use truth tables to understand whether a formula is always true, right? So we call it a validity or tautology, right? So that's if the rightmost column of the truth table is always true, the rightmost column being sort of the output of a formula, then we say that that's a tautology. If it is all false, then we call that a contradiction, right? And if it has some true values and some false values in the output, then we call that as a satisfiable formula. Okay, so there was the last problem that was added to your assignment was on understanding these terms, right? Validity, satisfiability, and contradiction. So we also talked about how logical formulas using certain operators can be converted into a normal form. You also have a problem in your homework which asks you to take operations involving one operator and turn it into an operation involving a different operator. Okay, so these are some of the things that we learned about propositional formulas. Okay, so again, this is a unit on propositions. So the formulas are called propositional formulas. Okay, now then we talked about proofs. We talked about axioms, which are things that we take for granted, and inference rules, which are special types of axioms, but they allow us to deduce something from, they allow us to combine what we know and derive new things, new formulas based on formulas that we already know to be true. Those are called inference rules. And then we talked about formal proofs, which is simply a way of stating, okay, here are the axioms and here are the inference rules that I use at each step. And by doing that, at the end, I arrive at a proof of something. Okay, so then we spent so the first part of your homework is concerned with propositions. The second part of your homework one is concerned with proof techniques. So we went through how to prove an implication, how to use proof by cases, and how to prove by contradiction, right? So we had of these, I would think that proving an implication and proof by cases are fairly straightforward, which doesn't necessarily mean that you will always get a proof by cases, but it is, other things being the same, proof by cases is generally easier to do than, say, proof by contradiction. And proof by contradiction, again, some of you or many of you may have trouble with it because it just maybe the whole reasoning in proof by contradiction may seem confusing, and we'll get to that later on in the course. Right? So we will talk about another proof technique called induction or mathematical induction, and it is often a proof by contradiction is really a contrapositive of an implication that you can prove using induction. So in a sense, this proof by contradiction and proof by induction are really two sides of the same coin, but most people will find the induction proofs much more intuitive in terms of understanding why the proof works versus a proof by contradiction, which again may take some time to get used to. Okay, so so that's brings us to the end of this unit on propositions. The next unit is called predicates. Okay, so let me see how to. Okay. So now we are moving forward to section 3.6 in your textbook. Okay. So a predicate is like a proposition, but it has a placeholder, right? So we put the placeholder or a parameter, as we call it, in parentheses, and we say, so remember when we're talking about propositions, we just said P, right? And P was a proposition. In the case of a predicate, we are still going to have a name for the predicate, but then the predicate will have some parameters, right? So in this case, there is a single parameter called n, and the statement is going to say something about n, right? So in this case, we are defining a predicate which holds for numbers that are perfect squares, right? So we can say P of n consists of 0, 1, not 1. And so on, right? So P of n, I shouldn't say consists, which is wrong. P of n holds because P of n, once you plug in the value of the parameter, right, then it becomes nothing but a proposition, right? So suppose we substitute, 1 in the place of n, then the right-hand side becomes 1 is a perfect square, right? So we could also substitute 3, and then it becomes 3 is a perfect square. So you can see that, this is a true proposition, and this is a false proposition. But the point is that once you fill in that parameter, then it becomes a proposition, right? So that's what a predicate is. A predicate has one or more parameters, but once you substitute those parameters, then the resulting statement is a proposition. Okay, so that's how we define and understand a predicate. Okay. So if the predicate takes so if the predicate takes a predicate may take one or more arguments, right? So if it takes one argument, then we call it a unary predicate, where unary comes from one, right? So if it takes two arguments, then we call it a binary predicate. If it takes three arguments, we'll say ternary predicate, and so on. Okay. We rarely go beyond that. So but if you do, then we will just say k-ary predicate if it has k parameters, right? So so here is a predicate we are defining called py. The py predicate has three parameters or three arguments, as we would call it, and it has this form, right? It says p of py holds if the arguments to py are Pythagorean triple, right? So x squared plus y squared equal to z squared. Then, so once again, we can say, py of it's been too long since I did these problems, so I can't even immediately think of triple. So that is true, right? But that is true, and that's not true, right? So that is false. Okay. So a predicate can have any number of arguments, and these arguments are called or are said to be are called variables, right? And they are specifically known as free variables to denote the fact that they are there are no constraints on what values they may have. You are free to give them different values and then check whether the resulting statement is true. So again, if you have questions, you should, again, if you're going to talk among yourselves using chat, that's great. But I usually have a hard time, keeping track of what is on the chat. Once in a while I'll see and then I'll answer, but other times I won't. So yeah, so just wanted you to know. So again, the best approach is to unmute yourself. Unless of course I ask you to lift your hand, then you can raise your hand, and then I can pick up, and then I can ask you to answer a question. But otherwise, if you need to get my attention, just unmute and talk. Okay, so we say that x, y, and z are free in this statement to denote the fact that you are free to give them some values, and then after that, all the free variables are given values, then you can evaluate, because what you have at that point is a proposition. Okay. So we define the term satisfiability and validity in the case of propositional formulas, right? So what is a propositional formula? It consists of logical operators, but the components themselves are just propositions, which means that they are either true or false, right? Whereas in the case of predicate, we have variables that that can be arbitrary. In this case, these variables are integers, right? So they are not just true or false. So there is a generalization when we go from propositions to predicates, which is that in propositions, we talk about each proposition taking the value of either true or false. Now, here, these parameters may take values over different domains. So in this, very often the domain of interest for us will be integer domain, but there could be other domains too, right? But most certainly, we are not going to be talking about true and false as the values of variables in the case of predicates. Okay. Other than that difference, that is the variables in the propositional formulas. Once again, propositional formulas are the ones that we talked about until the last lecture, right? The variables, which we simply call them as propositions, those variables take only two values, true or false. Here, the variables may take many different values. But the notion of satisfiability is still the same. Can you find some way to assign values to these variables such that you end up having a formula that is true, right? So for instance, this is a satisfiable predicate, right? Because here is an example, right? We can assign 3 to x, 4 to y, and 5 to z, and that makes this py predicate to be true. So that's the meaning of saying that something is satisfiable. Okay, so it's satisfiable if you can find some assignment of values to the variables such that the definition becomes true. Okay. Now, validity is also the same thing, which again, in the propositional case, we said when something is valid, what we said is that no matter whether you set the propositions to true or false, all possible combinations, the formula itself will be true, right? The same way here we are saying that take those variables, no matter what value you assign to them, the proposition, the statement will always be true. Okay, so for instance, let's define an example. Q of x comma y, which we can define to be right. So that is a valid predicate, right? So Q of x comma y is valid because no matter what value you assign to x and y, this statement is going to be true, right? So that is called a valid predicate, right? And so again, the notion of satisfiability and validity are not any different from what we have discussed in the past. Okay, so now, again, the definition says there exists at least one value for each variable such that the formula is true. Okay, and if all assignments make the predicate false, then we would once again call it a contradiction, right? So so we already said that PYXYZ is satisfiable. We also gave an example of a Q, which is valid. We can also define an R of X right? So if we said R of X is defined as X greater than X, well, again, that's false for all, and then if we are thinking about X being the domain of natural numbers, then we can say that X greater than X is going to be false for all natural numbers. So this will be a contradiction. So any questions so far?
Yeah. when it comes to the free variables and the satisfiability, is it satisfiable? Like, are you checking one variable at a time, or are you checking all three variables?
No, you
together?
first need to give some value for every variable. Until you
okay.
do that, it's not clear how to check how to say whether something is true or false.
Got it. Okay. And then if even one of the variables doesn't work, it is not satisfiable. Like in that scenario.
No value assignment for these variables, right? You have tried every possible combination of values for these variables.
Yeah.
And in all cases, it ends up being false. Then you say it's a contradiction.
Got it. Okay.
That it is unsatisfiable, right? Again, the term unsatisfiable and contradiction are the same.
Got it. Thank you.
Okay. Any other questions? Okay, so here is another example of here is another example of a valid predicate, which says that if y greater than 0, then x plus y is greater than x, right? So that's again, always true, no matter what values of x and y you choose. This statement is always true, right? So this is an example of a valid statement, right? So so now we come to something special in the case of predicates, which are called quantifiers. Okay, so quantifiers allow us to say something is true for every value of some variable, or that the formula is true for some value of a variable. So for instance, we could say for all x, x square greater than or equal to 0. Okay, so this is the for all symbol, right? So it says for all, and this thing says there exists. Okay, and so this statement says that there exists a value of x that makes 5x squared minus 7 equals 0, right? Now, I could have also said there exists an x in natural numbers such that 5x squared minus 7 equal to 0, right? Now, this existentially quantified formula is valid, right? And this is what?
Invalid.
Pay attention to the set from which x is chosen, right? So the first formula says that x is a real number. Okay, so you may not be familiar with those those symbols, but this is the symbol for real numbers. Okay, and this is the symbol for natural numbers, right? Natural numbers are 0, 1, 2, 3, 4, right? So all integers equal to or above greater than 0, right? So pay attention to that and then tell me.
Is the second one unsatisfiable?
Right, it's not satisfiable because it's only, this one is satisfiable because, the solution for this, right? When you set x equals 7 divided by 5 square root, right? That is the value which makes, that is the value of x that makes the statement true, right? And clearly, this is not an integer, right? So therefore, there is no way to find an integer to satisfy that equation, right? So this is So this is valid, but that is unsatisfiable. Okay, I'm going to, abbreviate because it just takes too long to write, right? So that's unsatisfiable. So sometimes we will abbreviate. So for instance, we could say, for all x, comma y that are, natural numbers, x greater than or equal to y, or y greater than x, right? So the abbreviation is that I'm using a single for all, although there are two different variables. Okay, so whereas if I have to write out the long version, then I would have to write something like for all x in natural numbers, for all y in natural numbers, x greater than or equal to y, or right. So I have to write that slightly longer version, and then I may abbreviate this way. Okay, it's not. Okay, so this is the notion of universal quantification, which means for all, and existential quantification, which means there exists. Okay, so so we say that a quantifier captures or binds a variable, right? And as a result, that variable is no longer free. Okay, so if you look at just that formula, right? For a moment, ignore everything outside of the box. Okay, so n equal to x square has two variables, right? So one is n, the other is x, right? So it has two variables. But when you say there exists an x such that n equal to x square, then this x, the value is already somehow, being picked by this quantifier. So what we say is that this quantifier binds the variable x. So as a result, the only free variable in the outer box is just n. Okay, that is why we say that this is a predicate on a single variable n, and it basically says whether this variable n is a perfect square or not, right? So again, it's a predicate, which means that for some values, P of n will be true, and for other values, P of n will be false. Any questions so far? So we are going to go through some examples, taking some English sentences and trying to, state that, capture that as a quantified logical formula.
Can you explain again, like what it means for the variable to be bound?
Okay. So you put a quantifier, right? The quantifier says there exists some variable, right? So we say that this quantifier binds this variable. Okay, and therefore that variable is not free anymore. And the notion of free is, well, it's not something that you can just plug in some value and check, because this formula says as long as there exists some value of x, then this formula is true, right? So the only thing that is left for you to plug in is just n, right? So what was free in the inner box, right? X is a variable that's a free in the inner box, but when you get to the outer box, you no longer have to pick a value for x. Okay, the quantifier will kind of pick the value for you, and you only need to pick the value for n. Okay, so let's look at more examples, and then if it's still not clear, we'll come back. Okay, So every American has a dream. Okay. So we can use the predicates d of y to denote right. So it's basically d of y is a way of saying that somebody has a dream, right? So we from the context, we assume that there can be many dreams. So we want to sort of capture that dream as a parameter, right? So we say d of y. So every American, so we need to say, a of x to say x is right. So whenever you are asked to, take an English statement and turn it into a logical formula, the first thing you have to do is to kind of find its components and introduce either predicates or propositions to capture those components, right? So once you do that, then we can turn this into a logical formula. Does somebody want to try? So this is something that's going to use, for all and there exists, right? And, a of x and d of y. Anybody wants to try? Okay, so let's go ahead and I'll write it out. So maybe next example is something that people will feel more comfortable about trying. So every, right? The word every suggests for all, right? So because we can also say, so we can say for all x, right? Okay, let's try it differently. Okay, so I'm going to change the setup here just a tiny bit. Okay, so I'm going to say dream. So we are going to define a set of dreams called D. Okay. And then we are going to define set of so this is the notation I had before is a little bit more clumsy than this one. Okay, this is simpler. So we can say that for all x in A, there exists a D in D such that x dreams of D, right? So that would be a logical formula corresponding to this English statement. Okay. We could have also tried there exists a D belonging to D such that for all x belonging to A, x dreams of D. Which of these do you think is a closer match for the statement?
The first one?
Yeah. Go ahead, please.
I said the first one.
Why do you think it is the first one?
Probably just the order in which it's written.
So what's the difference between the first and second? Let's start with that. Someone else wants to try telling me what's the difference between the two statements.
Well, the second one sort of implies that there's one dream that applies to every American rather than just every American has a dream.
Right. So the first one says that each American has a potentially different dream. The second one says, all of the Americans have the same dream. Okay. So, but it is not entirely, one might say that the first interpretation is more likely to be correct than the second one, but we cannot categorically rule out the second statement because we often talk about the American dream, right? So if you talk about the American dream, then it's not unreasonable to, say something like this and mean this, okay? But of course, the problem is that we are trying to illustrate here is that when you just say it in English, there can be ambiguity. And when you say it as a formula, that makes it, much more clear. At least it exposes the fact that there could be ambiguity and then forces you to be more clear, right? Okay, so let's try a different quantified statement. Every even integer greater than 2 is the sum of 2 primes, right? So this is what we called as Goldbach's conjecture in one of our first, in the last Thursday. So let's first, write it out to be a little bit more clear, right? So we say that for every even integer n greater than 2, right? So we are being a little bit more explicit, okay? So we introduce a parameter n, and we say n greater than 2. It's the sum of 2 primes. Then again, we introduce the parameters p and q. Now we have a formula that has 3 parameters n, p, and q. Okay. So now, can someone tell me how to? Does someone want to take a shot at turning this into a formula? You can raise your hands. Well, yeah. So I'm still a little bit slow.
You could say P, like capital P is the set of primes.
Okay, we can do that in English. So let's just say we'll do it in English.
Okay.
So just tell me the quantifiers first.
For all n in the set of natural numbers, I guess.
Right. So n. Okay. Right. Then.
There exists p comma q in the set of natural numbers.
Right. So we'll be okay. P comma q in. Right. Okay.
Such that.
Okay. So we will say. P and Q are prime. So again, the main thing is to get the quantifiers. The rest of the thing can be more or less in English. It's not that important. Okay, because that's not our goal. Our goal is to, expose the quantification that's going on in this English statement.
What about the n is greater than 2? Would you include that after the n is in the set of natural numbers?
You're right. Very good point. Right. So I should not have missed that. So the way to say that is, right, because what it's saying is that for every even integer n greater than 2, what it is saying is that if n is greater than 2, then there exists primes p and q such that n equal to p plus q, right? So that's why we have to turn it into an implication. N greater than 2 implies, or rather we could, let me try this. Right?
Also, don't we have the restriction that n is supposed to be even?
Yeah. Very good. So I'm being careless, and I'm glad you are recognizing and fixing those mistakes.
So should you like generally put that after you like define what the like variable is in? So like write that after the n, or should you write that after the such that?
So in this case, right, what we are saying here is that this assertion needs to hold only for even integers greater than 2, right? So we would typically put it right here as an implication, right? Because this is a condition, because if the condition is not true, then we don't care. We are not trying to say anything if the condition is not true.
So would you do the same with the p and q are prime, or just keep it where it is?
If you turn it into an implication, that is not that is not saying anything like what we want. Okay, because if I turn this, right, so if instead of this, if I said that okay, that's a completely different formula, because now I can pick p and q to be non-primes, right? Then this implication just becomes true, right? So the formula doesn't say that if p and q are prime, then n equal to p plus q. It says that there exist two prime numbers p and q, right? It doesn't say if these numbers are prime, only then n needs to be equal to p plus q. It just says they're, it is predetermined that there must be two prime numbers. If you turn it into something like this, then it's saying nothing, right? It becomes a vacuously true, right? Because there exists, all you want is to pick p and q such that this whole implication becomes true. And again, we know that in any implication, if the antecedent is false, right? If the antecedent is false, then the whole implication becomes true. So to make this, this thing into true, all we need is to pick p and q that are not prime. And that's really not saying anything like what the theorem is trying to say. Okay, so let's try changing the order, okay? And let's say if instead of using this, we just said can someone tell me what this formula means and whether it makes sense? You can again raise your hand and I'll try again whether I am able to, respond quickly enough. Okay. Yeah, go ahead. Okay, Greg.
I don't think this makes sense because this would imply that there is a single input PQ that for every single n would be able to add up to n, but we can clearly disprove this with a simple example, like
right.
2 plus 3 won't make 6, for example.
Right. So this is complete nonsense, right? Because this just cannot be true, right? So sometimes if you have if you're not sure which order of quantifiers to use, you can write down in both ways and recognize that one of them really doesn't make sense, and so you have your answer. But there will be other times when you may still be not sure, and then, well, you can just hope that you'll get better, right? Or it could be a fundamental problem in the sense that the statement that you're given is very ambiguous, and then you just cannot turn it into a formula because it's genuinely not clear which order of the quantifiers is implied. So that brings us to this question of order of quantifiers. Sometimes the order doesn't matter. So for instance, if you said for all x, for all y, x greater than y or y greater than or equal to x, right? We can flip around x and y like that, and it doesn't change the meaning of the formula, right? But we saw several cases where if you have a for all and a there exists, then the order does matter, right? Because if you move the there exists outside, then that becomes a stronger or more difficult thing to hold as opposed to when you have the there exists inside, right? Because in this case, you pick an n, and then based on the value of n, you can pick p and q, right? So that seems easier, whereas here you have to first pick a p that's going to work for all values of n, right? And it seems much harder to find those types of p and q that are going to work for all numbers, right? So for instance, no, I want to give an example. Okay, so the order often matters, but there are some cases like two for alls or two there exists. It doesn't really matter. the relative order doesn't matter if the quantifiers are of the same kind. Okay, but if the quantifiers are of a different kind, then often it matters. There may still be cases where it does not matter, but in most cases, if you have two different types of quantifiers next to each other, if you flip their order, the formula means something totally different. Okay. Okay, so the next thing is how do you negate quantifiers? Okay, so I guess it's close enough to 4:20, so I'll stop here and then take any questions. And to say a little bit about what the plan for next lecture is, we are almost at the end of predicates, and we will go through the next unit is about sets. Okay, so some of you made a comment about what is high school math. So although I use the term high school math, what I mean is math that you studied in school, right? And a lot of things that we are talking about here are actually based on math you studied in school, but unfortunately, a lot of the math that you learned in lower grades has been forgotten because the curriculum didn't really build on some of those concepts. So one of the things we try to do here is try to pick various concepts you have learned over time and try to connect them, and hopefully that connection will help you remember them in the future and remember them for the long term, right? So things won't, it becomes less easy to sort of learn something this semester and forget it in the following semester. We want to sort of build on, what you learned before and show you the connections that help you retain that in your head for a long time. Okay. Any questions?
Yeah, could you go back a slide? I was curious about the other two order rules, the order of quantifier slide.
Yeah.
Oh, okay. So I did not see that second part. Okay, thank you.
Yeah. Okay. Any other questions? Okay, so I will see you on Tuesday. Have a nice Labor Day weekend.
Thank you.
Okay. I will end the session.